So we're changing our schedule a little bit. We're starting on the hour from now on, so some of you might need to U of T time, starting 10 after. So we're going to be starting on the hour at 10 tonight. So I want to introduce our speaker before we start. Our speaker today is Lauren Hetherington. And she grew up in the Maritimes and got her Bachelor's of Science at the University of New Brunswick. Now she's studying tidal streams, and those are the formations of matter and stars that are created after globular clusters and or galaxies merge. And tonight, sorry, is that enough?
That's fine.
It's good enough. And tonight she's going to be talking to you about dark energy and dark matter. So, oh, and one other thing, she's going to graduate soon, and this might be her last talk. So thank you for giving so many talks over your years.
So, hi there. Is everyone able to hear me? Can you hear me fine at the back? Awesome. I see thumbs up. Oh, I guess I should put my slides over here. That would be nice. That's weird. Okay. Technical difficulties. Anyway, my name is Lauren. I'm going to be talking to you about dark matter and dark energy. Hey, whatever, it's fine. We're talking about dark matter and dark energy. A good place to start is what's the universe overall made out of? So the first thing you might think of when you are thinking about what's the universe made out of is you might probably think about stuff like this. So like galaxies, which are made out of stars and gas and dust. You also might think about cats, or those of us in the room, or the room itself, the air we're breathing. All of this stuff, all of the matter that we interact with, we call that baryonic matter. And it all has some properties. It interacts with gravity, so everything that has mass is attracted to other things that have mass. There's also electromagnetism, where like charges repel and unlike charges attract, and you've dealt with this a whole lot if you've ever used electricity. And then there's these two other forces, the weak nuclear force and the strong nuclear force. For the weak nuclear force, as it's right in the name, it's very weak. It's on a very short distance that it works, and it has to do with the decay of nuclei. And then the strong nuclear force is what holds the nucleus of an atom together. But everything that we're familiar with and that we can interact with on a daily basis, that makes up less than 5% of the universe overall. So what's the rest of the universe? Well, first of all, there's this dark matter, which is, there's 5 times more of that than there is of baryonic matter. And then, but that itself is only about 30% of the universe. The rest of it is in this dark energy. So there's a whole lot of the universe that we don't really know much about. So I'm going to start with dark matter. So a good place to start is, what's the evidence for dark matter? And the easiest way to approach this is to think about how dark matter influences how things move. So, first of all, how are you going to measure how things move? The way you're going to do this is using spectroscopy. So you've probably seen this album cover before, which is a nice demonstration of this. You take some light, and then using a prism or grating, you break that light up into all of its components. And you generally get a nice rainbow. The other thing you get is, depending on what you're looking at is made out of, you can get these lines. And the particular lines you get depends on what it's made out of. You can sort of think of this as like a fingerprint of what you're looking at. But you can measure these in a lab and you can know where they should be. And then once you have that, you can observe things using spectroscopy. You can look at a star, for instance, and you can figure out how it's moving towards us or away from us. So let's say we're over here observing this star. It's emitting some light towards us. If it's standing still compared to us, then the lines are going to be in their usual place. If the star is moving away from us, lights will wave, and they're going to be shifted redwards. They're going to be redshifted. Conversely, on the other hand, if the star is moving towards us, waves are going to be compressed. Everything's going to be blue shifted. And here's sort of an animation to show an example of what that might look like. So this is an exaggerated planet size, but showing a star wobbling because of an orbit and what that spectrum might look like down here. So you can see when the star is moving towards us, all the lines are shifted towards the blue, and when it's moving away from us, everything's shifted towards the red. So one place you can look, one interesting place to look, and one of the first places that some evidence of dark matter was found, was in galaxy clusters like this one, or specifically this one. So this is the Coma cluster. So everything you're seeing here, except for those two, are galaxies. So everything you're seeing here is a galaxy. And this sort of density in the middle is a cluster of galaxies, which are all attracted to each other. So if you're looking at how fast a galaxy is moving, it's important to, you sort of have an idea on how fast a galaxy can move, because they're all being held together by gravity. If a galaxy is moving too fast, it's going to break free and just fly off somewhere. So Fredericton, this guy, made measurements of the Coma cluster in the 30s. And what he found was that galaxies in the Coma cluster were moving much, much faster than you would expect them to be. In fact, he made the measurements and then he did some math and he found that there should be 400 times more mass in there than there is if you actually just count up the galaxies. So later measurements show that number was higher than it should be by about a factor of 10, but like this was the first indication that there was, or the first good indication that there was definitely more mass than you might otherwise expect. So this was sort of corroborated or confirmed later on by looking at motion in another context. So looking at something called rotation curves. So what is a rotation curve? So an easy way to think of it is we're showing speed versus how far away from the center of whatever you're looking at is. So it's telling you how fast the parts of an object are moving. So let's say you have something rigid, like that disk or my hat. And if that's spinning, the middle isn't moving at all. It's stationary. The outer edges are moving very, very fast. And it's continuous from the middle to the edges. The whole thing is rigid, so it's linear. But then instead think about what does the rotation curve of the solar system look like. So in the solar system, as opposed to being a rigid hat or a disk, everything's being held together by gravity. In particular, everything, since the majority of the mass is in the sun, everything's orbiting around the sun. And not only that, as you're getting further and further away from the sun, you're going to be because the force of gravity is going to be weaker, you're going to be orbiting more slowly. So if you look at how fast the planets and dwarf planets and everything else in the solar system are moving, Mercury, it's closest to the sun, it's whipping around at a really high speed. And then if you look out at the outer edges, Neptune and Pluto and other things in the Kuiper Belt are moving at a relatively relaxed pace. What does this look like for a galaxy? Or like a spiral galaxy like our own, or Andromeda. So this person, Vera Rubin, and her collaborator she wanted to take a look at various spiral galaxies and make good measurements of their rotation curves. Folks had tried to do this before, but around the time when she was working, there were newer instruments that were more efficient than the ones before. So she went out on a study to measure several different spiral galaxies and see what all the rotation curves were. But before seeing what she saw, let's sort of think about what you might expect. So there's no dark matter at all, and the only mass that's there is what we can see. The overall structure of a galaxy, or a spiral galaxy, if you're looking at it edge on, you have this bulge in the middle, and you have this disk, which is pretty flat, and it tapers off towards the edges. So if you wanted to draw what a rotation curve for this might look like, does anybody want to take a guess at what it might look like in the middle? Okay. Pardon? Yeah, it'll basically be stationary in the middle, and since you're adding on mass as you move outwards, it'll sort of go up. Your speed will increase as you're moving out from the very center. But then once you're beyond a certain point, you're just adding on additional disk stars, and it's getting relatively sparse. So after that point, it starts to drop off. And then once you're even further away, it starts looking kind of more like what you see in the solar system, because most of the mass is inside of your orbit now. So what did Rubin actually see? So here's the plot from her 1970 paper. So as opposed to what you would expect if everything was in stars and gas, you do get that initial bump, and something weird going on there. But if you look at the outer edges and then compare that to how fast you're moving just outside the bulge, you're not actually moving any slower. The stars at the edge of Andromeda, this is for Andromeda, are moving about as fast as the stars right at the middle. And this wasn't a unique observation. This was seen again and again. So over Rubin's study, she looked at 21. So here's 21 different rotation curves stacked together. And more recent measurements have continued to see the same thing. So the details near the middle kind of vary, but like out towards the edges, we see the same flat rotation curve. So you see something like this red curve, which is quite a bit higher than what you would expect out towards the edges. So the way that you can make up for that difference is if you add in extra mass. So if you add in extra mass, that'll increase how fast your orbits are. But not only that, it can't be more mass added right to the middle. If you add more mass to the middle, you'd be bumping up near the middle and you'd still be dropping off. So it needs to be more mass that's spread through the galaxy and beyond. So the picture that we're starting to build here is that instead of galaxies just being this, you have that plus a spherical halo, we call it, of this unseen mass, this extra mass, which we call a dark matter halo. So what do we know about dark matter so far? Did you have a question?
Yeah, is dark matter distributed uniformly throughout the universe, or does it sort of coalesce around certain areas?
Yeah,
Galaxies then are formed.
Yeah, it coalesces. So, for instance, in the case of our galaxy, we have our galaxy within this halo of dark matter. And then you can sort of build up that structure. So you have larger halos for galaxy clusters and so on and so forth. So yeah, dark matter definitely coalesces. But anyway, so what do we know about dark matter so far? We know it doesn't emit or block any light. We also know that it has mass, because we're detecting it by its gravitational, we're detecting it because of its gravity. So this sort of ties us into, this sort of gives us a approach to probe for it more directly. So one tool that we can use is called gravitational lensing. So gravitational lensing it's a consequence of Einstein's theory of general relativity. And the way it works is, let's say you have a light source. You have this light source right here, and you have a telescope right here, and you're looking at that star or galaxy, and then there's a whole pile of mass in the middle. Doesn't really matter. Could be a galaxy, could be another star, could be, yeah, just a whole bunch of mass. So what you might expect is, sort of from your intuition, is this star is giving off beams of light in every direction, and that's not going to be affected by the mass. That's going to go, and it's going to keep on going and not be affected. But it turns out that actually what happens is that the light curves. The gravity actually bends the path of light. So what you're going to see now is, since you're sitting here at your telescope and you're looking this way, you're going to see the light from your star or galaxy coming from that direction and that direction. So if you trace those over, you're going to be seeing these two images of your light source. So this effect is called strong gravitational lensing. This gives you objects, or it gives you things kind of like this. So in this case, you can sort of think of it like you're starting from this and you're rotating it around. So every single path that you're looking, every place around here in this whole ring, the light's being bent and you're seeing the background galaxy from a different angle. So this is some background galaxy with a really massive foreground galaxy. But strong gravitational lensing, it turns out, is actually kind of rare. More commonly, what you'd see is called weak gravitational lensing. So weak gravitational lensing, unlike in the strong case where you have really obvious arcs, it's kind of hard to see if you just look at a single galaxy. You have to look at a whole bunch of galaxies and average them together. So suppose you have a whole bunch of galaxies. They're randomly oriented. I chose the angles of each one of these ellipses using random.org, so they are indeed random. But let's say there's some overall trend. And this could be caused by some big mass way below the screen. So if you look at an individual galaxy, you can't really tell what's going on there. But if you look at a whole bunch and you average them together, you can start to see a pattern. And you can work backwards from this to then find where the mass is that's causing the lensing. So what we have now is we have an observational tool which tells us where mass is. So we have a whole bunch of mass that we can't see directly, but now we have a way to look for mass. So now we can find it. So one really important example is called the bullet cluster. So here's an image of the bullet cluster in the optical in visible light. So once again, everything here is a galaxy, except for there's one star right there. Well, two stars, but and you have these two clusters, a large one and a small one. And just in the visible light, it's not necessarily that exciting. But what happens if you look at the gas? So if you look at this in the X-rays, now you can see where all the hot gas is. So both of these clusters, they're full of gas, and it turns out that there's more gas than there is in the galaxies. But anyway, the galaxies, if you look back here, the two clusters don't really look that perturbed. The reason is because there's so much space between individual galaxies that when the two clusters sort of pass through each other, it's almost like you have two crowds of people, but they're really spread out. So they just kind of walk through. Maybe a couple will interact, but overall, they'll just pass through each other. The gas, on the other hand, is pretty evenly distributed. It's like the air in the room, for instance. It's much less dense than that, but it's low density, but it fills everything up more or less constantly. So what happens is that for the gas, it reacts really enthusiastically when they pass through each other. You can see the larger of the two is kind of squished, and the smaller one is kind of plowing through and leaving a wake. So what you might expect, naively, if there's more mass in the gas than there is in the galaxies, if you use lensing to try and look for where that mass is, you'd probably expect to find it following the gas. But it turns out that if you look at weak lensing and you work backwards and you reconstruct where the mass is, so the blue right here is showing a reconstruction of where the mass should be located. It actually follows the galaxies. So just to give you an idea of what that looks like, or what exactly is going on here, here's just a video showing. Play. Anyway, whatever. Here's still frames from the same video. What you have here is you have the blue, which is the mass, and that's going to be your dark matter. And then the red is the gas. And they pass through each other. The gas reacts enthusiastically, whereas the dark matter just passes through. It doesn't really interact with itself or anything else for that matter. So what this tells us is that even though the dark matter is smoothly distributed, kind of like we would expect the gas to look like, it doesn't interact in the same way. It doesn't seem to interact with itself or the rest of the baryonic matter there. So we can add that to our list of things that we know about dark matter. So right after, doesn't emit or block any light. It's massive, and it doesn't seem to interact in any significant way, or at least not in any way that's detectable. So this brings us to our next question. What is dark matter made out of? We know it's there. What is it made out of? So one idea is called Machos, or massive compact halo objects, because astronomers really love acronyms, but anyway. So they're massive and dense objects that don't emit a lot of light. So this would be things like black holes, brown dwarfs, rogue planets, neutron stars, or like red dwarf stars as well. So like anything that's really small and dense would be a macho. So these satisfy what we know about dark matter because they're hard to see. They'd also satisfy they'd also act the way we see it act in the bullet cluster, because these are really small and dense, which means that if you have a whole bunch of Machos and a whole bunch of other ones, and these clusters pass through each other, most of them are going to miss. Almost none of them are going to collide or interact. But can we actually detect these? And it turns out we can go back and use gravitational lensing once again. Only this time, instead of a picture like this, because your Machos are much, much lower mass than a galaxy, the effect is going to be a lot smaller. And also, because the effect is so much smaller, you're not able to resolve the images anymore. They kind of blur together and make it so that the star you're looking at, the star behind the Macho, appears much brighter. Here's an animation of what that would look like. So here's our telescope. We're looking at a star, and then in this case it looks like a brown dwarf passes in front of it, and very briefly you have, so probably about on the order of days and weeks or months, you'd have two images, but you can't distinguish them. So what you see is you see the star become brighter. So you can look for these. It's really hard to look for an individual Macho and follow that. But what you can do is you can look at some area of the sky, and you can pay attention and see how often you see events happen like this unexpectedly. So folks have done this. So what you do, like once you've found some number of events, you can figure out, well, what's the probability of an event even happening, of one of these even happening, and then you can work backwards and say, how many Machos are there? What number of Machos would make that a reasonable number of events to count? So some folks have found various collaborations, like the Macho Collaboration actually found some number of Machos, or they exist, but not in nearly the large enough numbers. So they exist, but there's not enough of them. The highest estimate, which the Macho Collaboration put forward, was 20%, but for a lot of reasons that's kind of discredited, mostly because more sensitive experiments couldn't confirm that. So, but even if you take that at face value, Machos can't be the majority of dark matter. Another possibility, sort of counteracting or in opposition to Machos, are WIMPs, or weakly interacting massive particles. So WIMPs are subatomic particles, but unlike the atoms that we know and love, you leave out a couple of the forces. So WIMPs would only interact with gravity, because they're massive, and with the weak nuclear force. Which means that because the weak nuclear force works on such a small distance scale, over such a small distance, you're not going to have these interactions happen very often. Which means that you'd still expect to see what we saw with the bullet cluster, is if you have a whole bunch of WIMPs evenly distributed, the sort of target that they would have to hit to actually interact with anything is so small that it's going to be extremely rare. So can we try to detect WIMPs directly? So we can sort of take some inspiration, some direct inspiration from a similar experiment. Experiments that were done to detect neutrinos. So neutrinos are these particles that are generated, they're produced by the sun during nuclear fusion. There's some large number flying through all the time. And one experiment that was done to try and detect neutrinos was the Sudbury Neutrino Observatory. And that was essentially what they had was they had a gigantic vat filled with heavy water. And the idea was you have all this mass. Now and then a neutrino is going to pass through and interact with the nucleus, and then that'll generate a little bit of light, which then can be detected by all these light detectors. And this was successful, and this guy, Art McDonald, won a Nobel Prize for it in 2015. So SNO has since expanded. It's now called SNO Lab. So there's now several different experiments. They're all in a mine in Sudbury, 2 kilometers underground. There's many different experiments in there, several of which are looking for dark matter as well. But one that I find really cool is called DEEP. In particular, this version is DEEP 3600, and it's called DEEP 3600 because there's 3600 kilograms of liquid argon that goes into that container. So here's a schematic of what that looks like. You'd have a whole bunch of liquid argon in there. What you would expect is, or what's hoped is, if a WIMP passes through, liquid argon is pretty dense. It also would emit light. So if a WIMP hits an argon nucleus, the nucleus will recoil and a little burst of light will be produced, and then that'll be detected by the array of detectors that surround the whole thing. And it's a little bit complicated because you also have neutrinos going through here, but the way just the way the reactions to neutrinos versus WIMPs occurs, you can differentiate them. So this is just one experiment of many. There's a very long list. This is just a handful. So like DEEP and Picasso and IceCube and CDMS. Just to name a handful. Many of these are ongoing and new ones are being constructed. So we might find WIMPs soon. But whatever WIMPs are, they're not going to be something that's currently in our standard model of what matter in the universe is made. They're going to be something really completely new, which is exciting because as soon as we find WIMPs, or if we find WIMPs, we'll be learning something new and fundamental about the universe. So that's dark matter. I haven't talked yet about dark energy. So dark energy is this other 70% of the universe. So what is dark energy? It might be a little bit easier to instead approach this from a direction of what does dark energy do? How does it influence the universe? So dark matter is extra mass. It has gravity and it pulls on things and affects how they act, how they orbit. Dark energy pushes out. It makes the universe expand faster and faster. And I'm just going to jump right to the end. Currently the best description of what it probably is something called the Cosmological Constant. So what is that? So this was first introduced in 1917 by Einstein. So they were, Einstein and other folks were trying to describe how the universe worked. And at the time, the prevailing idea was that the universe is static. It's some size and it's staying that size and it's always existed. and stuff like that. So out of general relativity, what you would expect is you have mass and energy in the universe. That should cause the whole thing to collapse. It should contract, and that didn't really fit with the idea at the time that the universe should be standing still. So Einstein added in this additional constant called the cosmological constant as a constant energy density in the vacuum of space, which also has a pressure that's pushing outwards. What do I mean when I say an energy density of space? So if you think of it like if you have some clump of mass, mass and energy are the same thing. So effectively, you have some energy, you remove that, you just have a vacuum. But that vacuum has some intrinsic amount of energy to it as well. And that's constant, or would be constant through all of space. But of course, the universe isn't static. So it was just a little bit later on that Hubble showed that, oh, the universe is expanding. So from that it was decided, oh, okay, well, the universe isn't static, then we don't actually need a cosmological constant, it's just zero. Yeah, maybe expansion is slowing down, but you have that initial expansion and that just sort of keeps going. And this tends to get called, or Einstein called it his biggest blunder. But anyway, so the idea at this point is the cosmological constant is zero, the universe is expanding, but it's not necessarily expanding constantly. So at this point, some folks are starting to wonder, well, how does the expansion of the universe change over time? Is it always expanding at the same rate, or is it slowing down? Is the universe going to expand forever, or is it going to slow down and eventually turn back in on itself and end in a big crunch? So to get a sense for that, we want to measure, or try to measure the size of the universe throughout its history. And a way to do that is to measure the distance to really, really far away galaxies over time, over the history of the universe. So if you want to measure distances to really, really far away galaxies, you want to use something called a standard candle. So a standard candle it's some source of light, and you know how bright it is. You've measured how bright it is in some other context, and you know it's always the same. So you can look for this, and then if you see it really, really far away, and if you see it and it appears to be really, really faint, then you know it has to be really far away. If you see it and it appears to be really, really bright, then you know it has to be more or less right in your face. It's kind of like, let's say it's the middle of the night, and you see a motorcycle headlight, but you can't see the rest of it. You just see the light. You can kind of guess how far away it is based on how bright it appears to be, because you know how bright headlights usually are. And you can decide whether or not it's safe to cross the street based on that. So one really good standard candle, especially across the universe, is called type 1a supernova. So type 1a supernovae, what you have here is they come from exploding white dwarfs. So a white dwarf is the leftover core of a star, kind of like our sun, that's died. And if that's in a binary with another star, which is turning into a red giant, stuff from the surface of this star it's going to start piling onto the white dwarf. It's going to be pulled off the surface, and it's going to pile on the white dwarf. And at some point, when the white dwarf reaches a particular mass, it becomes unstable and explodes really violently. So because these are always happening for the same reasons at the same mass, type 1a supernovae are always at about the same brightness. You can figure out how bright they are. So you can use them as standard candles. So a couple of collaborations, the HiZ Supernova Search Team and the Supernova Cosmology Project. What they did is they looked at a large number of type 1a supernovae, and they measured how bright they are to get their distances, and also measured their redshifts. So in this case, as opposed to the redshift necessarily from a star moving away from us, I mean a redshift due to the expansion of the universe. So what you would sort of naively expect if the expansion rate of the universe is completely static, is always the same, it's constant, then distance should increase linearly with redshift. So this is Hubble's law. The further away something is, the higher its redshift in a pretty much linear manner. But if you see some deviation downwards like this, that's going to imply that the universe is slowing down. The universe's expansion is slowing down. And it might be a little bit unintuitive why that implies that the expansion of the universe is slowing down. So a way that I find it easier to think about is that redshift is related to the size of the universe at the time that the light was emitted. So redshift is 0, the universe is its current size, and then as you go to higher redshifts, the universe is smaller and smaller. Additionally, the distance that you measure with supernova, that's also going to be looking back in time, because that light that you're seeing takes time to travel that distance. So you can replace these axes so that you have the universe is really big over here and it's really small over here. And this is stuff from almost today and then early on. So the way I think of it is, if you're looking at a supernova that's this far away, and instead you measure its redshift as, rather than being the redshift that you would get at the solid line, its redshift is actually higher than you would expect. What that's implying is that at the time that light was emitted, the universe was actually, I'm going backwards here. The universe was actually smaller than what you would have expected, which means that in order to be the size it is now, at some point it had to have been going faster. So earlier on it was going faster and then slowed down a bit. So the HiZ Supernova team and the Supernova Cosmology Project, they were trying to see which of these cases it was. Is the universe going constantly, or is it slowing down, or is it slowing down enough that it might eventually crash in on itself? So what did they see? Instead they saw something more like this. So this is the figure from their paper. I was going to take their data and replot it so it's a little bit clearer. But this orange line is the case if the expansion was constant. So instead of seeing it deviating downwards, what they see is it deviates upwards. So that implies that the early universe was in fact larger than would have been expected if the universe was expanding at its current rate. So that means that earlier on in the universe's history, it was actually expanding more slowly than it is right now. So the expansion of the universe is accelerating. It's actually speeding up. And I kind of gave that away earlier, but the explanation that seems to fit Einstein's biggest blunder actually turned out to be pretty all right. The cosmological constant exists after all, and it's speeding up the expansion of the universe, this additional energy density that's pushing outwards exists after all. So dark energy is really weird. So just really briefly to talk about why it's weird. So if you just have the matter that we think of, like normal matter, if you have a whole bunch of it, and then you expand it, you still have the same amount of stuff. It's just more spread out. It becomes less dense, but you still have the same total amount of stuff, the same total amount of mass. But dark energy is a constant energy density in a vacuum. It's just, it's intrinsic to space. So if you have some bunch of it and then you expand it, you're adding more space, which means you're adding more dark energy. So as opposed to having the same total amount that gets spread out, as you expand, you're getting more and more of it. So you end up with this loop where the universe expands a little bit, the amount of space you have becomes larger, which means the amount of dark energy you have also gets larger. Dark energy is pushing outwards, which makes expansion go faster, and then it just repeats, and the universe starts expanding faster and faster, which is weird, but anyway. So just to summarize, because I'm basically out of time, so I talked about dark matter, and we know it's there largely from its gravity, the way it influences things. And we have a few possibilities of what's made out of. There's more than these, but the ones I focused on were massive compact halo objects, so like black holes and neutron stars and things like that. And they exist, but there's not enough of them. Another possibility is weakly interacting massive particles, which would fit the observations very well, but we haven't detected them directly yet. But we're working on it. And whatever we find, when we find them, they're going to be something totally new. And dark energy is responsible for the accelerating expansion of the universe. Rather than just expanding at a constant rate, it's expanding faster and faster. And it fits really well if we call it this cosmological constant. But that isn't necessarily a satisfying answer. And in fact, we don't necessarily know if the cosmological constant is actually going to be constant. It might, yeah, that's sort of an open question. So more research is needed for both of these. So thank you.
Okay, we have some time for questions. Anyone have a question? Okay, we'll take one in the front here.
You said that as the universe expands, energy increases, dark energy increases, right?
Mm-hmm.
So whatever happened to conservation of energy, conservation of mass, and all these things that we learned as students?
Okay, so
where the energy is coming from, if you say it increases, coming from where?
that's a really good question. So the question was, how does dark energy fit in with conservation of energy? That's a really good question. I'm not actually sure the answer to that. It seems to be somewhere where that doesn't quite work out. But, sorry?
It has negative pressure, so it does negative work and expand.
Okay, so
We have another grad student right here who
That's how I would explain it.
studies more. So can you repeat what you said?
Yeah, so the dark energy has negative pressure. So as it expands, it does a negative amount of work to expand. And that compensates for the extra energy. It's very non-intuitive. But fluids with negative pressure are very non-intuitive.
Another question? Can we take one on the far side?
If dark energy and dark matter are not embodied, then why do you think that terms like mass and energy that have worked with embodied matter, why do you think that those analogies will also work when dealing with something that's completely new?
I'm sorry. Is your question, how can we say that dark matter is...
Like, why are we using the analogy of matter and energy when we're talking about dark matter and energy? Because it seems like we've only had some observational evidence of how it works. But why do we, like, why is it of such that when upon seeing this thing, the first reaction that we have is like, oh, it's a binary analogy.
Right, so like why do we call dark matter matter and dark energy energy when they're probably new things, or they're new things. So with dark matter, like it behaves in a bit of a weird way because we can't see it and it doesn't seem to interact, but it still has mass in the same way that regular matter is. So whatever it's made out of, it's made out of physical stuff. It's a different type, but it's still a form of matter. From everything we understand about it, it is a form of matter. For dark energy, why do we call it energy? And the reason for that is because it works as an energy density in space. It's if you describe it as an energy density for a vacuum, and that has negative pressure, like it is a type of energy.
So it just fits better with the equation?
Yeah.
Okay, do you have another question?
Yes, you were mentioning that dark matter seems to be found or attracted to galaxies. Number one, is it anywhere else? Number two, does it have anything to do with the black hole in the center of a galaxy? And could it be somehow influenced by that? Is there any indication of that?
Okay, so number one was.
Is it anywhere else other than, would that be part of the clue of what it is in terms of how it behaves if it's only there and nowhere else?
Right. So first of all, it's a little bit. We sort of talk about like the way I think I might have said it was you tend to see it clumped around galaxies, but it's a little bit. That's kind of a little bit backwards. So in our best models, what you start off with is a more or less smooth distribution of dark matter and regular matter with really slight deviations. So the dark matter clumps and then the normal matter falls into that. So it would have started off everywhere and then sort of fallen into the places where it was slightly more dense. So we would sort of expect it to be everywhere. It's just more dense around galaxies and clusters.
How I like to think about it is galaxies are near dark matter, not necessarily dark matter is near galaxies. So the dark matter was there first, and then the baryonic matter goes there.
Mm-hmm. And
take one more. Did you want to pick?
You also had a second question about.
If there's, we've spoken many times about maybe not with every single galaxy, but it seems fairly often that there's a black hole in the middle of a galaxy, and I'm curious if that gives any more hints or clues as to where it comes from, how it all fits together, or do you just discount? Is it just two completely different animals?
it's like there's a lot we don't quite understand about how you form supermassive black holes in the centers of galaxies, but they would probably form the same way, where you have a whole bunch of dark matter, a whole bunch of matter, and then they probably form by matter falling into the center of that. So they're probably related in the same sense as like you have this gravitational well and stuff is falling into it. But yeah, possibly not more than that.
So do you want to take the last question?
Yeah, sure.
So, do we know if dark energy is like a separate thing that affects regular space, or is it maybe just a rule of space-time that it expands itself?
So the question was, is it some separate?
Like how matter affects space-time because mass makes gravity, which affects curvature of space and time. So it's a separate thing affecting space-time. So is dark energy that, or is it just like a law of physics that the universe, space-time itself expands itself without any help from anything else?
So it doesn't work the same way as just regular matter. Doesn't.
Yeah, like it would affect it does affect the curvature. It's like the. Sorry. Yeah, sure. It affects things, but it sort of fits into the same like.
Well, it means like time isn't like you can't have a model of time that affects space. Time is woven into the fabric of space. So is dark energy woven into space-time and affecting it that way?
Like an eccentric property of space-time.
Yeah, I think this is a conversation that we should continue afterwards.
Yeah, maybe come talk afterwards.
Theoretical. But before you guys leave, I just want to have a few announcements about what's going on for the rest of the night. So those of you who have tickets to the planetarium shows for 10:15 or 10:30, the meeting area for those shows are by the elevators. We also have standby tickets, so if you wanted to see a planetarium show at 10:45 or 11, I'm going to be giving those out here, so just come up and get tickets if you wanted to see those, and those also meet at the elevators. The telescopes are open tonight, and it should be clear. So to get to the telescopes, you want to go to the 14th floor with the elevators and take the stairs up to the top. You won't miss it. And lastly, we have some pencils up here for you to return your feedback forms, and I'm also going to put out some cookies to incentivize you to return them. Have a good night, everyone. Thank you.